Welcome everyone. Today, we'll explore how to count Squarefree numbers up to 2025 using the Möbius function. Let's dive in. Last time, we proved that the density of Squarefree numbers is about 6 over pi squared.
So today, we actually count them up to 2025 to see that formula in action.
Exactly. We will use the Q of x formula to get an exact value for Q of 2025. At the center, you see the formula for Q of x, a weighted sum over d squared up to x, where the Möbius function controls the sign of each term. Q of x simply means how many integers between 1 and x are square-free, that is, not divisible by any prime square.
So for today, our job is to plug in x equals 2025 into that sum and actually compute it.
Once we have the exact count, we will compare it with the prediction from the density 6 over pi squared and see how close they are. By the end of this example, you will see how that abstract density law turns into a concrete, computable table. If you only had a computer, you could just mark every Squarefree number up to 2025 by brute force.
Right. You could test each integer for divisibility by prime squares. But that sounds like a lot of checking by hand.
Because 2025 is 45 squared, the sum for Q of 2025 only needs d values up to 45. The slow approach would be to go number by number, checking for each n whether some prime square divides it.
So the amount of work grows with every integer up to 2025, which is tedious without a computer.
Our formula, in contrast, only needs us to consider d values whose squares stay at most 2025. So d runs from 1 to 45. And as we will see next, many of those d values instantly drop out because their Möbius values are 0. This is the payoff of theory. We trade a long, naive list for a much shorter, structured computation. To shrink the work even further, we need to remember how the Möbius function behaves.
I remember it can be 0 or plus or minus 1, depending on the prime factors, but I forget exactly when.
This definition says that if any prime square divides d, then the Möbius value is 0. And otherwise, for Squarefree d, it is plus or minus 1 depending on how many distinct primes divide d. So any d that contains a squared prime factor gives a term of 0 in our sum and can be ignored.
That means for Q of 2025, only the Squarefree d values between 1 and 45 can actually affect the total.
Out of the 45 possible d values, only 29 are Squarefree. The other 16 have Möbius value 0. For each Squarefree d, the Möbius value is either plus 1 or minus 1. So the sum becomes a careful balance of positive and negative contributions. Next, we will list those d values explicitly, splitting them into the plus 1 group, the minus 1 group, and the zeros. Let us organize all d up to 45 according to the sign of their Möbius values.
Seeing the whole list at once should make it easier to track where each term in the sum comes from.
First are the Squarefree d values with Möbius equal to plus 1. Each has an even number of distinct prime factors, or in the case of 1, no primes at all. Next are the Squarefree d with Möbius equal to minus 1. These have an odd number of distinct prime factors, usually a single prime, except for 30 and 42, which have 3.
Finally, these d values are not Squarefree at all because some prime square divides each one, so their Möbius values are 0, and they drop out of the sum.
With this classification in hand, we are ready to build a table of contributions for Q of 2025. Now we turn the abstract sum into a concrete table of numbers.
So each row will correspond to one value of d, with its Möbius value and its floor term.
Here is our formula specialized to x equal to 2025. Notice that d only runs up to 45. For each d, we record its square, its Möbius value, the floor of 2025 divided by that square, and then their product, which is the contribution to Q.
So the 16 non-Squarefree d values become blank rows, since multiplying by 0 leaves the total unchanged.
For instance, d equals 1 gives a term of 2025. d equals 2, 3, and 5 give negative terms of 506, 225, and 81. And d equals 6 and 7 give plus 56 and minus 41. Continuing this process for every Squarefree d up to 45 produces a full table, which we will now summarize rather than reading row by row.
So the hard work is really just careful arithmetic in that table, making sure each floor and sign is correct.
Instead of adding 29 numbers in a random order, we can group them by sign.
Right. Adding all the positive terms together and all the negative terms together should reduce mistakes.
These d values have Möbius equal to +1, so their contributions are positive. Adding the corresponding table entries gives a positive subtotal. When we add those positive entries carefully, for example by grouping big and small ones, we get a total of 2,135.
These are the d values with Möbius equal to -1, including both primes and the composite numbers 30 and 42.
Their contributions are negative, and adding them gives 905 in magnitude. So subtracting that from the positive subtotal yields Q of 2025 equal to 1,230. We now have an exact count of how many Squarefree numbers lie between 1 and 2025. Let us step back and compare our exact answer with the theoretical prediction.
This is where the 6 over pi squared density and the big O of square root x error term come in, right?
The general result says that Q of x is roughly 6 over pi squared times x, with an error that is at most a constant times the square root of x. If we multiply 2025 by 6 over pi squared, we get an estimate of about 1,231 Squarefree numbers.
Our direct computation gave Q of 2025 equal to 1,230, which is just one less than that estimate.
The actual error is around 1, while the square root of 2025 is 45. So the error really is small compared with the big O bound. This shows that the density 6 over pi squared is not just an abstract limit. It gives a very accurate prediction even at a modest size like 2025.
It is cool to see the theory and the exact arithmetic lining up so closely.
To practice, let us repeat the method for a smaller number where the arithmetic is lighter.
So we can make sure we understand the steps without being overwhelmed by big tables.
For Q of 50, the sum runs over d whose squares are at most 50, so d goes from 1 up to 7. First, list the Squarefree d values up to 7, namely 1, 2, 3, 5, 6, and 7, and compute each floor of 50 over d squared with its Möbius sign. If you carry out that computation, the contributions add up to 31, so there are 31 Squarefree numbers between 1 and 50.
When I group the positive and negative contributions separately, even for Q of 50, it feels easier to add them and to see how cancellation is happening.
Being fluent with this Möbius sum for Q of x prepares you to tackle much larger ranges and deeper questions about how Squarefree numbers are distributed. Thanks for watching this. Subscribe to Thinking in Math for more topics. We welcome your feedback, leave questions and suggestions in the comments.